Hi, this is Mr. Mack. We're going to talk in this video about graphing rational functions. Well, if we're going to graph rational functions, let's describe what a rational function is. Now, a rational function, say f of x, is going to be equal to the ratio of a numerator and denominator, where the numerator is a polynomial function and the denominator is a polynomial function. Now, one of the things that we'll be wanting to talk about is the degree of the numerator and the degree of the denominator. I tell a really bad joke sometimes by telling people that once Arnold Schwarzenegger finished being governor of California, he was going to make a movie for the math teachers, and we were going to call it The Denominator. Anyway, that is pretty bad. Now, if you have a polynomial, let's just look for example for a second. P of x equals, let's say x cubed plus 6x squared minus 19x plus 4. The degree of this polynomial, which is a polynomial in x, is the highest exponent on x in any term in the polynomial. So when we talk about the degree of the numerator or the degree of the denominator, we're just talking about this number right here. All right. So now also, if p of x is equal to like x plus 2 times x minus 3, realize that when you multiply those together, you would get x squared minus x minus 6. So the degree of this polynomial would be 2 in this case. And so if we were looking at something like this, we would still consider the degree of that polynomial to be 2. Now, there are certain features of rational functions graphs that it's definitely necessary for us to identify. One feature is where the vertical asymptotes are. Now, we were introduced to asymptotes and vertical asymptotes in the last section, but let's just formally say right now, the vertical asymptotes are the x numbers that make the denominator equal to 0 and not the numerator. That's probably poorly stated. Let me see if I can do a better job on that. If you have a polynomial function, p of x over q of x, let's just make one here, and let's say f of x is equal to x plus 2 times x minus 3 over x plus 2, x minus 5, x plus 4. Now, if you'll notice, when x is negative 2, this binomial right here becomes 0. And when you multiply 0 by anything here, that will still be 0, and then times this, you'll still get 0. So when x is negative 2, the denominator is 0. But now, when x is negative 2, the numerator is also 0, because this binomial, x plus 2, is 0 when x is negative 2. And if you multiply that by this number, whatever it is, you'll still get 0 in the numerator. So if you get 0 over 0, that's not going to give you a vertical asymptote. We'll talk about what happens there a little bit later. But when x is, say 5, this binomial right here is 0, and 0 times anything is 0. So your denominator will be 0, and your numerator won't be 0. So x equals 5 is a vertical asymptote. See, places that make the denominator 0 but the numerator not 0 are vertical asymptotes. Now, also notice that when x is -4, the denominator is 0 and the numerator isn't. So this function, f of x, will have two vertical asymptotes. One will be the vertical line x equals 5, and the other will be the vertical line x equals -4. I'll be back. Hi, I'm back. Now, as I recall, I was saying that anytime the denominator of a rational function was 0 and the numerator wasn't, that gave you a vertical asymptote. Now, there's a couple of things. X equals 5, for example, makes this denominator 0, and x equals 5 is the equation of a vertical line. That is the equation of an asymptote. So anytime you have a rational function, if you set the denominator equal to 0 and then solve that expression, you'll get equations that will be the equations of the vertical asymptotes. Now, when the numerator is 0 of a rational function and the denominator is not 0, what you end up getting is a place where the graph crosses the x-axis, because if you think about it, any fraction where the numerator is 0 and the denominator isn't gives you 0. For example, 0 over 5 is actually 0. So that would be y equals 0 at that particular point. And so you can find the x-intercepts by setting the numerator of the rational function equal to 0. You can find the vertical asymptotes by setting the denominator of the rational function equal to 0. And as long as you don't get 0 on the top and 0 on the bottom, in other words, when you have the denominator 0 and the numerator not 0, you get a vertical asymptote. Now, the second feature of a rational function that we need to talk about is horizontal asymptotes. Now, I'm going to get rid of this, and let's put 2 horizontal asymptotes, A-S-Y-M-P-T-O-T-E-S. Now, the horizontal asymptotes are almost exclusively a function of the degree of the numerator and the degree of the denominator. See, now, the horizontal asymptote will be y equals 0. In other words, the x-axis, let's just put here AKA. AKA stands for also known as the x-axis. When the degree of the denominator is greater than the degree of the numerator. So anytime the denominator degree of a rational function is bigger than the degree of the numerator, you end up with a horizontal asymptote that is the x-axis, or y is equal to 0. Now, if the degree of the denominator equals the degree of the numerator, then the horizontal asymptote will be y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So let's see if I can't just write an example up here. For example, if you have y equals 3x squared plus 6x minus 2 over 5x squared minus 7x plus 1, then the horizontal asymptote will be y equals 3/5. see, the degree of the numerator is 2, the degree of the denominator is 2. The leading coefficient, in other words, the coefficient of the term that has the highest degree in the numerator is 3, and the term that has the highest degree in the denominator is 5x squared, and its coefficient is 5. So the horizontal asymptote would be y is equal to 3/5. So that means as you go farther and farther out to the right and farther out to the left, the graph will be curving toward, it will be approaching the horizontal line y is equal to 3/5 in that particular case. Now, if the degree of the denominator is one more, or no, excuse me, I'm sorry. If the degree of the denominator is 1 less than, I'll go away here. If the degree of the denominator is 1 less than the degree of the numerator, then you're going to have what we call an oblique asymptote, A-S-Y-M-P-T-O-T-E. Now, an oblique means slanted. Okay, and finding those oblique asymptotes will take a little bit of work. Let's see if we can't go ahead and find an oblique asymptote. So let's imagine, let's just go to the next page. Let's imagine that we have f of x is equal to x plus 2 times x plus 1 times x plus 3 over x minus 2 x plus 4. Now, notice the degree of the numerator here is 3, and the degree of the denominator is 2. So in this case, we have a situation where the degree of the numerator is 1 more than the degree of the denominator. So, what have we got? Well, actually, this denominator is going to be x squared plus 2x minus 8. And the numerator, this may take me a moment, is x squared plus 3x plus 2 times x plus 3. And that becomes x cubed. Now, I have 3x squared plus 3x squared, that's 6x squared, plus, now, I have 2x plus 9x, that's 11x, and then I have plus 6 over x squared plus 2x minus 8. Okay, so here we go. We now have a situation where the degree of the numerator is 1 more than the degree of the denominator. First of all, we know, as long as I haven't made a mistake, that we have vertical asymptotes at x equals 2 and x equals negative 4. Now we also know that we have zeros at negative 2, negative 1, and negative 3. What on earth have I done to myself here? Okay. Well, let's see. If we put 0 into this function, we get negative 6/8. Notice when you put 0 in, all of the terms containing x's go away. So you have a 6 in the numerator, negative 8 in the denominator. Now that's negative 3/4. So 0, we're down here at negative 3/4. So I am guessing that this in the middle is going to go down here like this. It's going to come up, across the x-axis, down, up, and like this. Now, we need to know what happens outside. To find the slant asymptote, what you do is you take your rational expression and you divide your denominator into your numerator. Now, let me do that. Oops, get down there. What on earth? There we go. Now we're dividing. Oh, what happened to I had, what was that, x cubed? Yeah, x cubed. There should be an x cubed here. So what we're going to do is we're going to divide x cubed plus 6x squared plus 11x plus 6 by x squared plus 2x minus 8. And this is polynomial long division, something that we learned a while back. So here it comes again. You look at x squared and you look at x cubed and ask how many times is x squared going to x cubed? Well, it goes in x times. Now we multiply. X times x squared is x cubed. X times 2x is 2x squared. X times negative 8 is negative 8x. Now what we're going to do here is we're going to make one mark on each term in the second polynomial, and we're going to add them. So we get 0 here. We get 4x squared plus 19x, and we bring down our 6. Now, the question is, how many times does x squared go into 4x squared? Well, it goes in 4 times. So we put plus 4 up here, and again we multiply. 4 times x squared is 4x squared. 4 times 2x is 8x. 4 times negative 8 is negative 32. Now once again, we make one mark here on each term and then add, and we'll get 0 there, we'll get 11x there, and we'll get 38. So we write this as x plus 4 plus 11x plus 38 over x squared plus 2x minus 8. Now, here's the cool thing. For the oblique asymptote, we ignore this part. And we just take this part. So the oblique asymptote in this case is going to be y is equal to x plus 4. So if we go back up to our original graph here, if y is equal to x plus 4, we have a line that looks something like that. And now what we need to do is ask ourselves, we need a value over here, like at 3, for example. So if we put 3 in here, let's use the calculator. So parentheses x cubed plus 6x squared plus 11x plus 6, close paren on the numerator, divide, open paren on the denominator, x squared plus 2x minus 8, close paren, second quit. Now, if I ask for y1 of, what did I say, 3? I get 17. So for 3, we're up here someplace move this up out of the way some. We're up here at 17. And now I also, let's see, -1, -2, -3, -4, -5. I also need to know y1 of -5. So second, enter. And instead of 3, I'm going to put -5 in there. And I get -3. So I'm going to be at -5. I'm going to be down here at -3. Now, that's enough information to know that up here, the graph asymptotes there, comes down, and then turns around and asymptotes with this line. And here we've got one going like this, and then around again like that. So that's what that graph should look like. Now, if we were to actually ask the calculator to give that, to graph that for us, let's see what we can do. We need the window to go from at least -7x to 5x, scale of 1, and the y-min, -10 is going to be good enough for the y-min. The y-max is going to have to be about 20 for us to get all of this, and y-scale of 2 maybe. See what we get. Now, notice one thing that we did have trouble with here is the vertical asymptote at x is equal to -4, and the vertical asymptote at x is equal to 2. The calculator actually put that in. So on some of the newer ones, the calculator knows that those asymptotes aren't supposed to be included, and sometimes it doesn't, but that's kind of difficult. But notice we do have over here to the left, down towards the bottom, that part, and then this other part that I showed you up over here at the top. It's not really clear about the oblique asymptote though, so let's do this. Let's make the window go out farther, -15 for x min, and maybe 10 for x max, and then we're going to have to go y min -25 to y max maybe 40. Problem is you're going to see the end part, but you see, and okay, let's do this. Down on the next line, let's put in x plus 4. And so notice that line goes in, and can you see how x plus 4, that line does make it look like it's an asymptote after a while, but you can't really tell what's going on in the middle on that particular window there. So that's what we have with oblique asymptotes, okay? Now back here, so what else have we got? Oblique asymptotes. One more thing that we need to talk about is point discontinuities. Now, when you have a function, a rational function, where the denominator is 0 and the numerator is 0 at the same time, you get something that is 0 over 0. And when that occurs, at that particular point, there's a little hole. It's just a point discontinuity in the graph. Now let's take a look at an example of that. The example I'd like to use is f of x is equal to x cubed minus 8 over x minus 2. Now if we were going to graph this one, one of the things that we could do is we could just put this in our calculator and get a whatchamacallit, a table of values that we could graph. So we've got x cubed. If I get rid of all this stuff in the middle, minus 8 divide x minus 2. And we'll just clear this one out. Now, on this one, let's have the window go from -7 to +9, and 1 is a good scale, and let's go from -5 to +20. 2 can be a good scale there, and here's the graph. Now, if you look at this, we've got a parabola here, but and the graph isn't showing this, but if we were to ask for, if we were to ask what the value is at x equals 2. In other words, if I put 2 in, notice there is no y value for 2. And let's just do this. See, f of 2 is 2 cubed minus 8 over 2 minus 2. Now 2 cubed is 8, 8 minus 8 is 0 on the top, 2 minus 2 is 0 on the bottom. So now, at that one point, and I guess I kind of messed up here on the window. Let's try this. Negative 7 to 11 here, let's say. And now graph it. Ah, there we go. Now notice, at x equals 2, there's a missing spot in the graph. There's a hole, or a point discontinuity. Whenever you get a rational function where the denominator is 0 and the numerator is 0 at the same time, you get a point discontinuity. Now, the calculator here hasn't done a real good job of it. What you should have is something that looks like this, with a hole right there, and then it goes on around like that. Now, a lot of times we would like to know what the location of this hole is. In other words, we would like to know where the graph isn't, if you will. Now, one of the ways to do that is to just squeeze in on it. In other words, if you go to second window, or second window, table setup, and if you go down to the independent variable and go over and change this setting to ask, second graph gives you a table, then you can put values in for x and it will tell you what y is. Now if you put 2 in, it's going to say error, there is no value because it's 0 over 0. So if you put 1.99 in and 2.01 in, notice that those values are really very, very close to 12. And if you look back at the graph, notice that the two values, the two parts of the graph are kind of squeezing in towards a particular point. And when you look back at the table, you can kind of infer from this that that point is the point 212. So 212 would be the place where the graph isn't. Now, you can also locate this algebraically, and we'll spend more time on this later, but for right now, just remember, x cubed minus 8 is actually the difference of two cubes. It factors into x minus 2 times x squared plus 2x plus 4. And we've got an x minus 2 on the bottom. Now earlier you learned that you could actually cancel these things out, but when you did, you had to write x is not equal to 2 because that was the 0 of the thing that you canceled out. But at this particular point, if you put x equals 2 in for this, notice 2 squared is 4, 2 times 2 is 4, and 4 is 4, and 4 plus 4 plus 4 equals 12. So algebraically, you can find the location of that point discontinuity as well. Now, that covers the concepts that are involved in graphing these rational functions. Finding the horizontal asymptotes, finding the vertical asymptotes, oblique asymptotes if they occur, when they occur, and finding zeros, and then plotting some other points and plotting some graphs. That will be covered in the solution videos, so I do challenge you to watch the solution videos for this section. And that takes care of graphing rational functions.